Hello everyone, in this video we will learn all about similarities of triangles. Now given this figure, quadrilateral ABCD is similar to quadrilateral EFGH. So by the way, this is the symbol for similar. So their sides here, we have here 15, 12, 6, and 9. For the smaller quadrilateral, it's 5, 4, 2, and 3. So in this case, the scale factor of the sides, it's 3/1. So meaning the sides of the bigger quadrilateral, it's divided by 3 in order to get the side measurement of the smaller quadrilateral. So another, we have here triangle ABC. It is similar to triangle DEF. So take note, the number of rotation ray would mean that the two angles are congruent. So angle A and angle D are congruent, angle B and angle E are congruent, and angle C and F are also congruent. So their corresponding sides. So we have here 10, 6, 7. In here we have 20, 12, and 14. So the scale factor here would be 1:2. So meaning the side measures of the smaller triangle, it is doubled in order to get the measurement of the bigger triangle. So in this case, when you say similar figures, their figures whose corresponding angles are congruent and their corresponding sides are proportional. Let's have this one. Solve for x and y. So given this, triangle ABC is similar to triangle D, E, and F. So find the value for x. So given here, 8 and 6, their corresponding sides are x plus 3 and x. So in here, we will have its proportion. So for triangle ABC, we have here 8/6. For triangle DEF, their corresponding sides are x plus 3/x. So cross multiplying this one, so we will have 8x, 6 times x is 6x, 6 times 3 is 18. Transfer 6x to the other side, and solving for x, that would be 9. So if this side here is 9, so the length for DE would be 12, because that's 9 plus 3. Okay, another. So given here, triangle EDC is similar to triangle A, B, and C. So find the value for x and y. So take note here, we have here x, that's opposite of angle E. So corresponding side of x would be 9, because 9 is the opposite of angle A and E are congruent angles. Now the common side given to the two triangles, we have here 15 and 25, and they're both opposite of angle ECD and angle BCA. So let's make its proportion. So for x, we have here x/25. Corresponding sides to that for angle APC. So x is opposite of E. So opposite of A here is 9, and opposite of 25 here. So that would be 15. So cross multiply this, and the value for x is 15. Now solving for y. So y/25. So y is opposite of D. So D is equal to B. So that would be 10/15. So simplifying this, so the value for y is 50/3. So please take note of that. Okay, now given this, again, quadrilateral ABCD is similar to quadrilateral EFGH. So the scale factor here again is 3/1, or 3:1. Now getting the perimeter of quadrilateral ABCD, we will have 15 plus 12 plus 9 plus 6, or that would be 42. While the perimeter of quadrilateral EFGH, that's 5 plus 4 plus 3 plus 2, or that would be 14. Now the ratio or the scale factor of the perimeters of the two triangles here, that would be 42/14, or we can simplify it as 3/1. So with this, if two polygons are similar, the ratio of their perimeters is equal to the ratio of their corresponding sides. another example. Given this, triangle ABC is similar to triangle A prime, B prime, C prime. So let's answer the following questions. What is the scale factor of the two triangles? So take note, we have here 5, 4, 3. In here we had 10, 8, and 6. So the scale factor here is 1:2. Now what is the area of the small triangle? So take note, the formula for area is base times height divided by 2. So 4 times 3, that's 12 divided by 2. So that would be 6 square units. Another, what is the area of the big triangle? So 8 times 6, that would be 48 divided by 2. So that would be 24 square units. What is the ratio of the areas of the two triangles? So in this case, that would be 6/24, or that would be 1/4. Take note, if two polygons are similar, the ratio of their areas is equal to the square of the ratio of their corresponding sides. So the scale factor of the sides, it's 1/2. So squaring this, we will have the ratio of the areas of the two triangles, so that would be 1/4. Let's have this one. So given this, triangle, the side here is A and this is B. So the ratio of their perimeters, it's A/B. So the ratio of their areas would be A squared over B squared. Now suppose if this side here is 8 and this side here is 5. So the ratio of their perimeters here would be 8/5, while the ratio of their areas would be 64/25. Given this, triangle ABC, it's similar to triangle XYZ. So take note, their corresponding angles. So angle A, it's congruent to angle X. So take note of their number of rotation rays. It should be equal. Then angle B, that's congruent to angle Y. And angle C, that's congruent to angle Z. Then for their corresponding sides, for AB, corresponding side to that would be XY. Then AC, corresponding side to that is XZ. And for BC, the corresponding side is YZ. So take note, when you say similar figures or triangles, their triangles whose corresponding angles are equal and their corresponding sides are proportional. Now, we don't really have to prove that all angles are congruent and corresponding sides are proportional for us to claim that two triangles are similar. Actually, there are different triangle similarity theorems. So let's start. So given these two triangles, so angle A is congruent to angle D, angle B is congruent to angle E. So in this case, these two triangles are actually similar. So that is based on AA similarity theorem that states two triangles are similar if they have two pairs of congruent angles. That's the first. Okay, another. So given this, angle A is congruent to angle D, angle B is congruent to angle E, and angle C is congruent to angle F. So with this one, these two triangles are congruent or similar based on AAA similarity theorem that states two triangles are similar if they have three pairs of congruent angles. Okay, another. So given this, we have here the sides 4, 5, and 6. And for triangle EDF, we have here 8, 10, and 12. So in this case, AB over DE is equal to AC over DF is equal to BC over EF. So substituting this one, we have here 4/8, 6/12, and 5/10. In which when you simplify all of this, it will equate to 1/2. So given this, these two triangles are similar based on SSS similarity theorem that states two triangles are similar if they have three pairs of proportional sides. Okay, another. So we have here 5 sides 5 and 8. For the other triangle, it's 15 and 24. And we have here angles that measures 80 degrees. So again, AB over DE is equal to BC over EF. So that would be 5 over 15 is equal to 8 over 24. When you simplify all of this, it will equate to 1 over 3. And angle B and E are congruent. So it would follow that these two triangles here are similar. And that is based on SAS Similarity Theorem that states two triangles are similar if they have two pairs of proportional sides with congruent included angles. So take note that's side, angle, and side. Now for right triangle similarity, so given this, angle R and U are right angles, and you have here QS over RS is equal to VT over VU. So substituting this one, that would be 10 over 8 is equal to 25 over 20. When you simplify this, we will end up with 5 over 4. So it would follow that triangle QRS is similar to triangle TUV. And that is based on hypotenuse leg similarity theorem, or that's HL similarity theorem, that states two right triangles are similar if their hypotenuse and leg are proportional. Okay, another. So given this, we have here angles B and E are right angles. AB over BC is congruent to DE over EF. So substituting this, we have 8 over 6 is equal to 12 over 9. When you simplify this, we will end up with 4 over 3. So with this, triangle ABC, it's similar to triangle DEF, and that is based on leg-leg similarity theorem that states two right triangles are similar if they have two pairs of proportional legs. Okay, let's have this. So given this, ABCD is an isosceles trapezoid. Prove that triangle DEC is similar to triangle BAA. So again, when you do this, making use of the two-column format, so we have the statement column and the reason column. So of course, number one, it's always the given. So ABCD is an isosceles trapezoid. So with this, we can say that DC is parallel to AB, and that is based on trapezoids. Bases are always parallel. And the third statement here would be angle EAB is congruent to angle ECD because they are actually alternate interior angles and they're always congruent. So marking them, we have this one. So next to that, angle DEC is congruent to angle BEA because they are both vertical angles, and vertical angles are always congruent. So with this, we can say that triangle DEC, it's similar to triangle BEA, and that is based on AA similarity, or that's angle-angle similarity theorem. So take note of that. Another. So given this, AB over AD, it's proportional to AC over AE. So prove that triangle ADE is similar to triangle ABC. So with that, again, with a two-column format, so always start with the given. So getting the two triangles, so we have here triangle ADE, and the bigger triangle, it's ABC. So take note of their corresponding sides. So with this, we can have the second statement in which it is angle A, it's congruent to angle A. That's based on that. The reason to that is its reflexive property. So with this, we can say that triangle ADE, it's similar to triangle ABC, and that is based on side included angle side similarity theorem. So take note. Another. So given this, R is the midpoint of QS and PT. Angles Q and S are right angles. So prove that triangle PQR is similar to triangle TSR. So making use of the two-column format, so we have here our given. So with this marking, we will get this. So with that, QR, it's equal to SR, and PR is also equal to TR. That is based on the definition of midpoint. So next, we can say that triangle PQR is indeed similar to triangle TSR, and that is based on hypotenuse leg similarity theorem. The Pythagorean Theorem. The Pythagorean Theorem states that the sum of the squares of the two legs is equal to the square of the hypotenuse. So when you say Pythagorean Theorem, it also only involves right triangles. So given this right triangle, so let's square its legs. So that would be this one for the other leg. So squaring this, we'll get this. And for the hypotenuse, we will get this one. So by the way, in a right triangle, the longest side is always the hypotenuse, and it's always opposite of the right angle. So again, squaring this, we will get this one. So if this is 3, so when you square, you'll get 9. This is B is 4. When you square, you'll get 16. And when you square this 5 here, that will get 25. So Pythagorean theorem, that would be a square plus b square equals c square, wherein c is the longest side. So substituting, so 3 squared plus 4 squared equals 5 squared. So 9 plus 16, it's indeed 25 equals 25. So take note of that. This is the Pythagorean theorem. So the primitive Pythagorean triple are 3, 4, and 5. So how come they are Pythagorean triple? Or it will always prove the Pythagorean theorem. Now, when you multiply the Pythagorean triple by a certain number, still you will end up with another Pythagorean triple. Like multiplying this one by 2, so 3 times 2 will get 6, 4 times 2 will 8, 5 times 2 will get 10. So 6, 8, and 10 are still considered as Pythagorean triple. 36 plus 64, that is actually 100. Or when you multiply this by 7, so 3 times 7 is 21. Times 7, 28, times 7 is 35. So 21, 28, and 35 are still considered as Pythagorean triple. Now, find the value of x. So given this, our x here is our hypotenuse because it's the opposite of the right angle. So that would be a squared plus b squared equals c squared. Substituting, we'll get this. So this is 144 plus 25. We're getting the square root to both sides. So the value for c here is 13. Or the value for x is 13. Okay, another. So in this case, the missing here is one of the legs. So substituting in the Pythagorean theorem. So we don't know the value of this. So a squared. So this is 16. And this is 20. So simplifying this is 400 minus 256. So getting the square to both sides. So the value for a here is 12. So the value for x here is 12. So take note of that. Now, Pythagorean theorem in real life. So a road intersection, James and Sarah's house formed a right triangle. From the intersection, James' house is 2 kilometers away and Sarah's house is 1.5 kilometers away. What is the distance of the two houses? So in this case, that would be a squared plus b squared equals c squared. So the distance of the two houses is this one. So substituting, so 2 squared plus 1.5 squared. So 6.25, getting the square root to both sides. So the value for c is approximately 2.5 kilometers. Okay, another. A 10-meter ladder is leaning against a wall. The foot of the ladder is 5 meters away from the wall. How high did the ladder reach? So, making use of the Pythagorean theorem. So, we don't know the height. So, our b here is 5 and our c is 10 squared. So, simplifying, getting the square root to both sides. So, our height here is square root of 75, or that's approximately 8.7 meters. Now take note, in a triangle, if C is the longest side and the other two legs are A and B, C square is equal to A square plus B square. That would be a right triangle. But if C square is lesser than A square plus B square, that would be an acute triangle. And if c square is greater than a square plus b square, that would be an obtuse triangle. So take note, it's easier to identify what kind of triangle is the given if the measurements are in angles. But if the measurements are in side lengths, you have to make use of this formula in order to identify what kind of triangle it is. So for example, if the side lengths are 30, 40, and 50, so what kind of triangle is this? So making use of this, let's substitute. So this is 2, 5 is equal to 900 plus 1, 6. So indeed it's equal, so therefore it's a right triangle. Another, if the given is 6, 7, and 8, what kind of triangle is formed with this? So substituting, again, our longest side here is 8. So that would be 8 squared equals 7 squared plus 6 squared. So simplifying this, 64 is lesser than 85. So with this, it is an acute triangle. Now, if the side lengths are 9, 11, and 15, so again, 15 is the longest. So 15 squared is equal to 9 squared plus 11 squared. So simplifying this, this is 225 is greater than 202. So with this, it is an obtuse triangle. So take note of that. A 30, 60, 90 triangle is considered as a special right triangle. So in here, opposite of 30 degrees, that's x, opposite of 60 degrees is x squared of 3, and the opposite of 90 degrees, which is the hypotenuse, is considered as 2x. So in a 30, 60, 90 triangle, the shortest leg is always half of the hypotenuse. So if the shortest leg is half of the hypotenuse, so the longer leg here is square root of 3 times the shorter leg. Okay, so given this, the shorter leg is the opposite of the 30 degrees. The longer leg is the opposite of the 60-degree angle, and the hypotenuse is the opposite of the 90-degree angle. Now, if the hypotenuse here is 12, the shorter leg would be half, which is 6. The longer leg is 6 square root of 3. Now, if the shorter leg is 30 degrees, then double it to get the hypotenuse, which is 18. And the longer leg is 9 square root of 3. Now, if the longer leg is 15, what is the shorter leg? Now, take note, the longer leg is equivalent to x square root of 3. So simplifying this one, divide by square root of 3, then rationalize. So the value for x would be 5 square root of 3. Now, if this is the shorter leg, double this to get the hypotenuse. So that's 10 square root of 3. Okay, now let's have this. Find the area of a vegetable garden in an equilateral triangle shape whose one side measures 20 meters. So given this, to find the area of a triangle is base times height divided by 2. Since the height here is not given, so we have to solve for that. So the height is the line from this side perpendicular to the opposite leg. So again, if this is 60, so since we divide, so this will become 30 and 30. Now, if this is 20, so the opposite of 30 degrees would be half, so that's 10 and 10. And of course, the opposite of 60 degrees here is 10 square root of 3. Now with this, we can find the area, which is base times height divided by 2. So that would be the base is 20 and the height is 10 square root of 3 divided by 2. So that's 100 square root of 3 meters squared, or that is approximately 173.2 meter squared. Okay, another. Isosceles right or 45-45-90 triangle is another special right triangle. Now in here, the two angles are equal, so it would follow that the two legs are equal as well. So with this, the equal legs, it's x, so to get the hypotenuse, that's x square root of 2. So again, we have here the leg, which is opposite of the 45-degree angle, and the hypotenuse is the opposite of 90 degrees. Now, if the leg is 7, so the hypotenuse here would be 7 square root of 2. Now, if the leg is 3 square root of 5, then its hypotenuse would be 3 square root of 10. Now, if the hypotenuse is given as 16, to get the leg, so again, our hypotenuse is x square root of 2 is equal to 16. So divided by square root of 2 times square root of 2. So that would be 8 square root of 2. Now, another way of getting the hypotenuse here, so since it's a right triangle, is we can make use of the Pythagorean Theorem. So since the two legs here are equal, so that would be x squared plus x squared equals the hypotenuse square, which is 16 squared. So simplifying, this is 2x squared is equal to 256. Divide to both sides, so x squared is 128. Getting the square root to both sides, so that would be 8 square root of 2. So again, either method will end up with the same answer. Okay, so let's have this sample real-life problem that involves isosceles right. A square-shaped handkerchief measures 16 inches on each side. Now you fold it along its diagonal, so you can tie it around your neck. So how long is this tie? So given this, so 16 and 16, so to get the hypotenuse, that would be 16 square root of 2. Okay, now let's have this similarities of right triangles. Now given this right triangle A, D, and B, so the legs here are A, B, and AD. Hypotenuse here is BD. And AC here is considered as the altitude to the hypotenuse. Okay, now with this, we can identify 3 right triangles, and actually they are similar to each other. Now, the biggest triangle here is triangle DAB. Another triangle is this one, so which is triangle DCA, in which the right angle is C. In the first triangle, the right angle is at A. And the smallest triangle here is triangle A, C, and B, in which the right angle is at C. Now, making use of these 3 right triangles here, in which they're actually similar, so making use of the first and the second triangle, so let's relate its leg and hypotenuse. So the leg here is DA and hypotenuse is BD. For the second triangle, this is DC over DA. So multiplying this one, so that would be DA squared is CD times DB, or that would be the square root of CD times BD. Okay, next. Now making use of triangle 1 and triangle 2 and relating its side and leg and hypotenuse. So that would be AB over BD, and the other one is BC over AB. So cross multiply, we'll get this, getting the square root to both sides. So AB is the square root of CB times DB. Now, relating triangle 2 and triangle 3, we'll get this. And making use of its sides, so our legs, that would be AC over CD. And the other one is BC over AC. So, cross-multiplying this, we'll get this, getting the square root to both sides. So, AC is equal to CB times CD. Now, take note, this DA and AB, they are actually legs of the biggest triangle, and AC here is considered as the altitude to the hypotenuse. So actually these two are bases for the similarities of right triangles, in which the first one is, so this is the original figure, so the altitude to the hypotenuse is the geometric mean of the 2 segments into which it separates the hypotenuse. So with that, AC is equal to the square root of CB times CD. And that's the altitude rule. Okay, the other one. So each leg, so the legs here are AB and AD. So each leg, so leg AD, for example, is the geometric mean of the hypotenuse BD and the segment of the hypotenuse adjacent to that leg. In this case, adjacent to AD is CD. Now, the other leg, we have here AB. So, AB is the geometric mean of hypotenuse BD and the segment of the hypotenuse adjacent to AB, which is BC. So, take note of this. Okay, so in summary, this is the geometric mean altitude theorem. So C here is the hypotenuse, which is m plus n. H is the altitude to the hypotenuse, which is the geometric mean of m times n. And A here is a leg, in which it's the geometric mean of hypotenuse C and the segment adjacent to that, which is m. And another leg B is the geometric mean of hypotenuse C and the segment adjacent to B, which is n. So let's have an example. Now, given this is a right triangle in which the hypotenuse is divided into 9 and 27. So to find x, so x is the altitude to the hypotenuse. It's the geometric mean of 27 times 9. So that would become square root of 243, or that would be 9 square root of 3. Okay, another. To solve for y, so y is a leg. So y is the geometric mean of the hypotenuse, which is 27 plus 9, which is 36, and the segment adjacent to y, which is 9. So simplifying this, getting the square root of 324, so y here is 18. Okay, another. Now, for z is the geometric mean of 27 plus 9, and the segment adjacent to z, which is 27. So square root of 972, so that's 18 square root of 3. So take note. Okay, another. So given this right triangle EDG, so the measures are 6, 8, and 10. So let's find the measures of the segments in the hypotenuse, which is EF and FG. So solving for FG, so again, making use of the leg rule. So 8 is the geometric mean of the hypotenuse 10 and the segment of hypotenuse adjacent to 8, which is FG. So with this is 64, 10 FG divided by 10, so therefore FG is 6.4. So if FG is 6.4, and since this is 10, so to find EF, so that would be 10 minus 6.4, which is 3.6. Okay, another. Now with this, we can solve for x. So x is the altitude to the hypotenuse, so which is the geometric mean of the two segments, 3.6 times 6.4. So simplifying this and getting the square root, so the value for x is 4.8. Okay, so that would be all. Thank you.